while we get it going. So you have a really good understanding of this stuff conceptually, and what we're going to do now is attach algebra to it, really heavy-duty algebra. So you know that force causes acceleration, and this is where I generally get down. So what causes the ball that I'm pulling out here to move? Me. What am I doing? Applying force. So what causes the ball on the other end to move? Force. What's applying that force? The other ball. We've got all this transfer happening. It's really simple, but it's also a really great, there are a lot of layers of stuff here. There's stuff that we won't talk about till chapter 6, embodied here. But force being applied to that and unbalanced is causing an acceleration. Why are they slowing down? Another force in play, and it's two actually. I heard somebody say gravity and friction. The force of gravity on these things wants them to be hanging directly downward. It's balanced by another force, because they're not falling, of these strings. There's also friction from air. There's a little bit of loss when they strike one another. It is kind of soothing, isn't it?
It is.
So there are a whole lot of things going on here. There are a whole lot of things embedded here. An unbalanced force causes acceleration. And an object has to be interacting with its environment to have a force act on it. Okay? Okay. We're going to, like I said, we're going to do this algebraically. You probably saw you should have seen F equals MA in physical science. We do, back under the old standards in the OGT, there were 3 equations that the state of Ohio said physical science students needed to have. F equals MA, PE equals GMH, and kinetic energy equals 1/2 mass volume squared. Those 3. That was all the state said you had to know. What the state said, physical science students had to know those 3. So this is going to form the basis for a lot of what we do in this chapter. You know, all those substitutions that we started to do in the last chapter, I have you do that. I have you build that skill for a reason. And we've talked about that repeatedly. We build that skill because now we're going to have a bunch of different expressions for force. And we're going to do a lot of substitutions and a lot of setting equal so that we can find various parts of the interactions. The SI unit for force is the Newton. You may have known that, though nobody mentioned that in the Everything They Know. So we'll just say it clearly and say it now. SI unit of force is the Newton. That's named for Sir Isaac. An interesting guy, a brilliant guy, a pretty strange guy, but that's a tale for another time. And 1 Newton of force. So you remember that we can make derived units. We can multiply and divide SI units and get derived units. 1 Newton is a kilogram meter per second squared. So I'll write that here for you. It's a kilogram meter per second squared. That is what a Newton is equal to. And actually, the front cover of the physics book has a whole sheet of those. Yes?
Same with your chair.
So if we do dimensional analysis, knowing that F equals ma, 1 Newton of force is the amount of force that it takes to get 1 kilogram of mass to accelerate at 1 meter per second squared. So if I have a 1 kilogram mass, and actually this is a 500 kilogram mass, but we'll pretend. If I have a 1 kilogram mass, the amount of force that I need to put on this thing to get it to accelerate at 1 meter per second squared is 1 Newton of force. Now, if I lift this thing up, well, we'll get there. So, if we do our dimensional analysis, then any time that you are looking at newtons and you want to do dimensional analysis with them, you have to remember that underlying Newton is that expression, kilogram meter per second squared. because you're going to rearrange stuff, and you can check yourself, and we'll get into some heavy-duty rearrangements. You can always check yourself knowing that that's the underlying units for newtons, for force. Okay. We said that force is really about the interaction of an object with its environment. And there are two ways that a force can act on an object. We have contact forces and field forces. Just like it sounds like, contact forces require what? Contact. Who's buried in Grant's tomb? Grant. Contact forces require contact between the objects. Me lifting that box of colored pencils over and setting it there, I was exerting a contact force on it. Pushing something is a contact force. Driving your car involves a contact force. What's the contact force? More basic than that. More basic than that. What actually makes the car move forward? Contact between the wheels and the road. Friction between your tires and the road surface. Making contact and moving the vehicle forward. This is why ice is difficult to drive on. There is a loss of frictional force between the tires and the road. So, field forces don't require physical contact. Gravity is the field force that you've lived with your whole life. Gravity is the field force we are most familiar with. And a field is a region of influence. So we will not in this class talk about magnetic fields, but they're the other really common field force. If you go on to take college physics, which many of you, generally, even if you only have to take 1 year of college physics, which I hate to tell you biology majors have to, most places, you'll get into magnetic fields and electrical fields. Actually, you don't do a lot with electrical fields in the first year typically. That's further down the line. Computer science, electrical engineering, you're going to do a lot with electrical fields. Those exert a force on objects. Okay? You don't have to be in contact. Okay. This is where the rubber meets the road, so to speak. Ha-ha! Rubber meets the road, tires, friction, driving your car forward. Never mind. Jingle, jingle, jingle. What's that jingly thing? So force is a vector, and I think a couple people mentioned that in their what do you know, that force was a vector quantity. Force is made up of, it's a derived unit. It's derived from mass and acceleration. Mass is scalar. Acceleration is vector. You multiply a vector by a scalar, you get a vector. You get a vector. Good. Yeah, that was a question on your multiple choice. So, good. With any vector, you represent it graphically, and force is represented graphically, and this is super important. You really can't solve the kind of problems we're doing without graphical representations. It was tough with projectile motion. With forces, it becomes impossible. It literally becomes impossible to solve these without a graphical representation. So there are two ways to represent force graphically. There are force diagrams and there are free bodies. I will do my best not to screw this up, but I guarantee you I will, and it's your job to, every time I do it, go, Moser, wrong one. So I always want to say force diagrams, but we seldom use force diagrams. A force diagram shows every single force that's acting on an object at the moment. It shows all the objects in the situation. So to do a force diagram of you sitting in a chair at a desk in this room. Well, we tend to generalize in physics, so you turn into a potato. You know, there are worse things to be. But we have to show you, we have to show the chair, we have to show the desk, we have to show the floor. We show that you are exerting, the earth is exerting a force downward on you, Earth is exerting a force downward on you, chair is exerting a force upward on you, chair is exerting a force downward on the floor, Floor is exerting a force upward on the chair. Desk is exerting a force back this way on you. You are exerting a force back this way on it. It gets really, really ugly really, really fast. Don't try to copy it all, because it's horrible. This is why we don't do these. They're hideous. There are so many forces in this situation. Let's see, what have I forgotten? Oh, I've forgotten this one, and I've forgotten that one, and I've forgotten that one. Yeah, it's awful. I mean, it's incomprehensible. So as we tend to do in physics, we simplify. And what we typically use, because again, we said this is just too crazy, we don't usually do force diagrams. What we typically do are called free body diagrams. You'll often see, if you look at any like YouTube videos or anything, you'll see FBD in physics discussions. FBD or FBD, it's not an official abbreviation, so there's no like official, it must be capitalized or not. Free body diagram. It only shows one object in isolation. It doesn't show all the objects that are exerting forces. It just shows that one object, and it shows the forces on that one object. So this is the wild, crazy, wacky force diagram. We're not doing it, so we'll just get rid of it. Whoops. Cut. Cut. To show a free body diagram of you sitting at your desk, again, we make you a potato or some other similarly roughly cylindrical object. We generalize forms. We show the force of gravity acting downward on you, the normal force acting upward on you. We're going to talk about normal force probably a little bit on Monday. If you're leaning on the desk, we might show the force that the desk is exerting on you, and we might show the force that the chair is exerting on you. And if you're sitting still, these are all going to balance out. They're all going to zero. That's a free body diagram. That's easy. We can do this. So that is a free body diagram. And we're going to practice drawing some free body diagrams. Okay, so general guidelines for drawing a free body diagram. The object is drawn in isolation. We approximate the shape. Like I said, we very often turn people into potatoes, just sort of a lump. We might go so far as to do this. If we're feeling really generous, for a car. We can. Sometimes I do that. That's a person. There's a recognizable cylindrical object with a sphere on the top. That's us. Positioning the object correctly is important. So when I say positioning it accurately, we're not showing it in reference to other objects. That's mostly for your purposes in drawing it. If you know, it's kind of like doing those multi-vector analysis problems where if you start drawing over here, you run off the paper. That's all we're talking about. When you draw and label forces, this is really critical. And one year I had 2 students who seemingly never got this. So I want to make sure we make it very, very clear from day one. All forces are shown as originating at the center of an object. That's critical. You typically label the forces with whatever information you have. You label their magnitude if you have it. If not, you label an expression for it. Whatever information you have about the magnitude of the force and what that force is, whether it's normal force or gravitational force. If I say that Zach is pushing on something, I can label that as force of Zach. We do that. And you want to make very certain that you show those forces going in the correct direction. So let's practice a free body diagram. Okay, we'll do this, then we'll actually do a free body diagram on here. These are not just useful, they're essential. Okay? They are indispensable in analyzing. All of that resolving vector work that you guys did, you're going to continue to do that with forces now, instead of accelerations, instead of velocities. So to practice this, let's see, and I need a few guinea pigs. Zach, since you've already been mentioned as being a force to be reckoned with, want to be a guinea pig? Okay. We'll take this whole first row.
Yes.
So one of you gets to sit in the chair.
The king himself.
Any of the three of you. You toss a coin for it. I don't care. I will take a picture. What I would like the other two of you to do is to stand on the opposite sides of the chair. We'll take a picture of the setup. That's good. That's good. We like that. And I want you to just hold on to the chair. I want you to exert a balanced force on it. So I don't want Zach to move, but I both want you to push a little bit. Okay. I'm going to take a picture. You all look so happy. This will be on YouTube for posterity, for the ages.
I'll show my grand.
Yes. If YouTube still exists, then.
It'll be on hologram.
Okay. All right. So, what we have here is Zach. We have Zach represented here. We have some forces on Zach. We're going to start to list them. So, Zach, name one force that you're feeling on yourself right now.
Gravity.
Gravity. Excellent choice. So we have the force of gravity on Zach. We're going to show this originating in the center of the body. And we're going to label it F sub G. F sub G. Now, if there was nothing else acting on Zach, he would be sliding down, well, he would be falling down towards the center of the earth at an alarming rate. Zach, do you feel like you're falling towards the center of the earth at an alarming rate?
Not yet.
Okay, good. So there must be another force acting to counter the force of gravity. As a matter of fact, Zach looks pretty much like he's staying right where he is on the y-axis. I don't see you floating up into the air. You're not levitating, are you? Okay, good. So what that means is that whatever force is acting upward on Zach has to be equal in magnitude to the force acting downward on him. We'll do a lot more of that when we start doing sum of forces. I'm going to cheat and tell you what that force upward is called. Well, you know, the weird thing about the way this chapter is organized, I love this book. I really think that this is a good physics book. I like the way they organize stuff. The one complaint I have is in this chapter, it's like the third section where they introduce everyday forces and you finally learn what gravity and normal force are. So we're gonna kind of circumvent that, jump that, and talk a little bit about them right now. So the force that's acting upward on you that counters gravity, we call normal force. And it's shown as F sub capital N. Normal force. So Zach has normal force acting on him, or he would be, like I said, plunging towards the center of the earth at an alarming rate of speed. Now, at the moment when we had these two nice folks pushing on Zach, there were some other forces acting on Zach. We would call them force of Schuyler, force of Tarik. Okay? Oh my gosh. Oh no, okay, never mind.
Oh, what?
Nothing. Okay, so one of those forces, go back to gently pushing on Zach so he doesn't move, but you're exerting some force. Which direction is the force of Schuyler acting on Zach? Point. Okay, that way. So Schuyler's over here. Her force is acting this way. Okay, so we would label this, we're going to label it S, or F Schuyler. So which way is Tarik's force acting on Zach? There's Tarik. There is the force of Tariq. Okay? So as long as those are balanced on the y-axis and the x-axis, Zach is not moving. We'll talk more about that when we do sum of forces. That is drawing a free body diagram at its simplest. You're going to have lots of practice on this because you're going to draw lots of free body diagrams. You guys can have a seat. Thank you.
I already am.
To let it sink for a second, and does this make sense to you conceptually, or do you have questions? Okay. So you're looking at which way the force is pushing, not where the force is originating from necessarily. So those are often in opposition. So when you look at a situation, you have to think about, well, which way is the force originating? Which way is the force directed? You know, where does it originate from? Where is it directed? Yes, ma'am.
So the arrows are always like outward.
Yes, the arrows point outward from the center of the body. So you know, it feels to us. Well, actually, we don't really feel gravity because we've evolved with the gravity we have, and so you don't really experience it because it's just background to you. But you could say, like, well, you know, you feel gravity pushing you down. But it's really, so the concept, this little dot in the center here, the concept is called center of gravity, and you've probably heard that expression. We will probably not get to the point of calculating center of gravity. We don't typically do that. But in any object, there is a center of gravity. It's the center of the mass. So we talk about things being top-heavy and likely to topple over. It means they have a high center of gravity. An object with a lower center of gravity tends to be more stable. And you'll kind of see why as we start to do more force analysis. Question?
And we never draw the forces, like we would never draw scalar or torque.
No. No. Not in a free body diagram. If we were doing force diagrams, yes. But in a free body diagram, we just draw the object that we're interested in. Yes?
Are we going into, or not like questions, but like examples of like a truck that's taller than the car, and if you're going so fast, is that something else?
That's something else.
Okay. You said center of.
Center of mass?
Yeah.
We don't really get to center of mass.
Ah, okay.
We don't really do center of mass.
Right. That's the first thing I thought of. I was like, oh.
Oh, and that's a great. Remind me when we start doing forces on slopes.
Mm-hmm.
We can have a conversation about it, but we're not going to do it mathematically.
Oh,
So, okay. Other questions on free body diagrams? Okay. Okay. This is one that you explored yesterday. Newton's first law, also called law of inertia, and objects, and you guys all pretty much know this. You're all able to state this, and the what do you know? An object, we often say, wants to stay in motion or wants to stay at rest. They don't want anything. They don't have brains. But objects maintain state of motion unless they're acted on by a force. And that force has to be unbalanced. I'm going to add that word. So we're going to go borrow Zach here. Yeah. Nope. Okay. So Zach was not moving right or left. He was not rising up into the air. He was not floating. He was not falling down towards the center of the earth. And that's all because the forces on him were balanced. If he had acted on if an unbalanced force had acted on him, if Skylar had doubled the force she was exerting, Zach would have started to move. Okay? And the tendency is inertia. You're all familiar with it from that perspective. Those, the Newton's cradle, the little balls on the Newton's cradle. What force did we say is slowing them down?
Gravity and friction.
Gravity and friction. And if there was no friction, the gravitational force would actually end up balanced. I'll stop them for a second. Would actually end up balanced by the force of tension on the strings. In a world with no friction in a vacuum, we could get them to go forever. but we have forces that act on them that counter their motion. Okay? And so, though they would go forever left to their own devices without those countering forces, those unbalanced forces, they slow down. This is hugely important, and we're gonna hammer this repeatedly. Net force is the sum of the forces on an object. The sum on all axes. Because they're vectors, so we can break them down, we can add them up. An object doesn't accelerate unless there's an unbalanced force on it. If an object is accelerating, it has a non-zero net force. If an object is not accelerating, it has zero net force. So right now, you, sitting in your desk, do you have zero or non-zero net force? Zero. If you're not accelerating, you have a zero net force. On the y-axis, the question that I will ask you again and again and again, is it sinking down into the earth? Is it floating up into the air? If the answer to that is no, then it has zero net force on that axis. Is it moving to the left or right? If the answer to that is no, it has zero net force on that axis. Okay? So we look at net external force a lot, and we're going to practice doing net force. As long as net external force is zero, acceleration is zero. Okay. Right now there are a bunch of different forces acting on you all at the same time. We sum those up on each axis, and that gets us our net external force. Same method as resolving vectors. So if I have, well, we're actually just going to do a practice problem. So we'll go to page 132. If you want to grab a book, 10 minutes is more than enough time. We're told that Dericles' physics book on the top of a drafting table inclined at a 35-degree angle. They actually give you a free body diagram. We're going to practice drawing a free body diagram together. So their free body diagram shows the forces on the book, find net external force, and determine if the book will remain at rest in its position. So we're looking to see if it's got balanced forces or if they're unbalanced. So the first thing we're going to do is draw that drafting table. It's at a 35-degree angle, so let's see. That would be 45. I guess that would probably be close to, we'll say that's about 35. Okay. And you can draw it in either direction, it does not matter. Now, the book, we're going to draw as just sort of a box. And we're told, I mean the diagram tells you, that there is a force of gravity on the book of 22 newtons. Now here's the important thing. Notice that this book is not on a flat surface. Doesn't matter how slopey it is, the force of gravity is always directly down into the earth. So, force of gravity is going to look, whoops, wrong color. Force of gravity is going to look like this. And we're going to label that Fg. We are given a magnitude. We're told that that is, whoops, 22 newtons. Now there's something odd here. What did we say the force that opposes gravity, that surfaces push back up on you with is? Normal force. Normal force. Normal force. Maybe the only normal thing in some days. You can always count on normal force. Not usually a big fan of normal, but I like normal force. I like not plunging towards the center of the earth. Normal force, this is also critically important. And we'll spend more time on it when we get into the section on everyday forces. Normal force always acts perpendicular to the surface. So normal force is going to look like that. Okay. And we're told that the normal force here is 18 newtons. And I didn't. The wonderful thing about drawing with the iPad is I can move the box when my things aren't lining up in the center. So they should be lining up coming out of the center of the box, the book. We're told that there's a force of friction on this book, and that force of friction goes up the table. I didn't draw a very straight line. And that force of friction is 11 newtons. So right there you've done a free body diagram. Now one of the things you can do, and if you're doing this on the iPad, it's really easy to grab different colors. If you're doing it on paper, you can use colored pencils. Color coding your forces can be really helpful. And you can draw them all in pencil and then lay a line over it. But you're going to have computations to keep straight here. So you remember how we said that the coordinate system is kind of arbitrary? We typically use up and down, perpendicular to the Earth, y-axis, surface of the Earth, x-axis. There's a trick that we use with forces. I'm going to introduce it to you right now. They don't talk about it explicitly in this problem, but they use it. When we have an object on a slope, the easiest thing to do, and I will draw this in a different color so it shows up, is to tilt the axis. So we say then that the x-axis is there, and the y-axis, and you can see now that my normal force line is not perfect by a long shot. So that becomes our x-axis, that becomes our y-axis. Yes, ma'am?
The 35 degrees doesn't matter.
Oh, yes, it does.
Okay.
We're coming to that. It matters a whole lot. You're going to be so good at doing these problems very soon because we do a lot of problems on slopes, because things on slopes are inherently more interesting from a force perspective than things on flat ground. We do lots of things sliding down things and things not sliding down things, etc. Okay, so you've now got that image of, I don't think there's a way to change the color on that without erasing the line, but anyway. So our x and y axes are actually tilted. The reason to do this is that now two of the forces that are acting on this object line up directly with an axis. The force of friction and the normal force now line up directly with the axis. We only have one force that has to be resolved into components, and that would be gravity. So what we're going to do, we're going to get to a certain point with this, and then we'll stop. We'll come back to this problem on Monday. So we'll finish this problem on Monday, and then we'll go over the tests. What we need to figure out is the angle that the force of gravity makes with the y-axis. Does anybody see it intuitively? Some people do. I never do. I always have to do the proof for myself every single year. I mean, I know it now. Can you see intuitively what that angle is?
Which angle?
This one. The angle between the force of gravity and the y-axis. Okay, so let's copy, nope. Let's copy just, hold on. Copy that, take just this to the next page. I'm going to paste it and I'm going to enlarge it. Okay, so I'm going to move the red line down to there. I'm going to superimpose those two. So you all see, I think, typically, that, well, I mean, I told you this is 35. you all would agree then, let me get rid of this scribbliness, that this forms a right triangle. So this is the complement of 35, right? This is 55. So what angle is left over here because, whoops, this forms a 90. 90 minus 55 is 35. So we're right back to this is another 35-degree angle. And we'll do that sort of proof thing over and over again because it's not always intuitive. I mean, you have two choices. You can just say, oh, I always know that, you know, the angle between that perpendicular to the horizon line and the x-axis is the same as whatever the slope of the surface is. I can never take anything for granted. I have to prove it to myself again and again and again until I can finally take it for granted. So we will do that sort of geometric proof repeatedly. Okay, that's where we will stop. And we'll pick this up, starting the calculations on Monday.